Hello everyone, welcome back. In this video, we'll be discussing about the third problem of today's weekly contest, minimum number of operations to sort a binary tree by level. The problem states that you are given a binary tree or you are given a root of a binary tree. Each node here has a unique value and in one operation, you can swap any two node of a single level. So in one operation, you can swap 7 with 8 or you can swap 7 with 5, but you can't swap 7 with 3 or 4 because you can only swap nodes at a single level. You have to return the minimum number of operations such that nodes at each level are sorted. So basically you can see here nodes are 4 and 3, which is not sorted. So you can just do a swap, it will become 3 and 4. So this level is now sorted. So you did one operation for this. Now similarly you will sort the next level, similarly you will sort the next level, and finally return the result of the sum of the number of swaps you performed at every level. So you have to do this in such a way that you will require minimum number of operations. Okay. Now, like hope you got the solution. Now let's look at how to solve this. Okay. So let's say this is a tree. Okay. It is very clear that we can divide the problem into smaller problem by traversing level by level, or uh, by that I mean what we can simply do, we can say that okay, I will just traverse this level once and I will collect 3 14 10 in a vector, let's say. Similarly I will traverse this level once and I will connect 5 4 2 1, and similarly I will traverse this level and collect 6 7 9 8. So after doing this, what we can simply do is apply some algorithm that will give us what is the minimum number of operation such that we can sort this 3 14 and 10 by just swapping two integers at a time, right? Similarly, you can apply the same algorithm here and you can apply the same algorithm here. Okay, so what is the problem reduced to? Problem is reduced to finding or writing a function that will return us the minimum number of operation to sort a particular array. And what is the operation? Operation is to swap any two integers in that array. Okay, so hope this point makes sense. Now finding out each level is a very standard BFS problem. You can do it with DFS as well, your choice. I am not explaining that here. I will touch upon that briefly while we are discussing code, but for now I am not explaining that. I hope you know that. Even if you don't know that, just look at the next problem that we are solving. That given a vector, return me the number of operations, that the minimum number of operations that needs to be performed to make the array sorted, and the operation is to swap two integers. So even that would be very helpful. Okay, so let's move ahead. So if you are a regular viewer of this channel, this problem we have solved somewhere around this problem very recently in one of the past lead code hard problems. So we have tried divide and conquer there. So what I thought, let's just try to apply the same here and see if it works and why, and if it doesn't work, why it doesn't work. Okay, so that you get some clarity. So let's say this is the array 9 10 2 5 6 9 7 1. This basically denotes that these are the integers in a single level as per the problem. Now this is the array, you have to just sort this array and return me the minimum number of operations that is required to sort this array. Okay, now we can just use standard divide and conquer. We will divide the problem into smaller problems equal sized. So we divide it into two smaller arrays. Then again this will be divided into two smaller arrays, and so on and so forth. Now if you remember, the the case where you can apply divide and conquer is determined by the merging part, because divide part is very simple, right? The only thing you have to do is you have to think about if we can come up with some algorithm that will help us merge two the solution of two problems. So what exactly it is? Let's say you, or let's talk about this level that will be easier. So let's say this, you have to solve the problem for this array 9, 10, 2, 5, or you need to find out what is the minimum number of operations required to sort this array. Now you've divided the problem into two parts and you solve this part and this part separately. Basically, you know what is the minimum number of operations that is required to sort this array. That is 0, right? And what is the minimum number of operations that is required to sort this array? Again 0, right? Now, now you have to merge it. Like you have to merge it so that such that you get the answer for the original question. Okay, that let's try that. So let's say you see that okay, I got a 2 here, right? And this 2 should come in the first place, right? Now if this 2 should come in the first place, what will come in place of 2? In place of 2, 9 will come, right? Now if 9 will come here, notice that we have found out what is the minimum operations required to sort this particular array, but we have seen that 9, like the new position of 9 is now this, right? So whatever we have solved for already is something that is changed, because we have solved for sorting 9 and 10, right? But now 9 comes here. So basically whatever we have solved previously is now not valid, like the problem is itself is not valid, right? So that's the main point of identifying whether you can apply divide and conquer. We can't apply divide and conquer here because we can't divide the problem itself into independent problems. Like these two are not independent problems, because whatever is here, if we swap it with some element here, it will affect whatever we have already uh, already discussed, or like whatever we have already solved for. Okay, so we can't divide the problem into smaller problems itself, so that's where divide and conquer will not be applicable here. Okay, now let's try to solve it. So this is our array. Okay, now think logically what exactly you have to do. You have to bring the smallest number here, right? Now you can think that okay, I can directly bring smallest here, right? Or you might also think that okay, uh, there might be some more cases. Let's say I swapped the smaller element. Okay, let's say I swapped the smaller element with this first, and then I swapped the smaller element with this first. So by doing this, maybe let's say 10 also comes at the last position. So you don't need to do anything afterwards, right? So you can think of something like this. Like this might be more optimal overall than just swapping this. Now the argument is it is never optimal to try two possible hops, even if it is solving something in the latter part of the problem. Okay, so this is a statement that I am claiming. Now let's try to prove it. Okay, so what we are saying is this kind of this kind of hop would never come. Like you will I directly go to, and one will directly go to its desired place. Now why? Let's say this hop come. What is the benefit you are getting? The benefit you are getting is 10 is now coming here, which is the correct position of 10. Okay, but think about it. If you directly moved 1 to 9, right? And let's say what will be the value in that case? 1 will become 9 and this would become 1, right? Now let's say you did that already. Now can't you just swap these two again to get the similar arrangement? Like this will become 9 and this will become 10. 10 is again at the correct position, right? So the argument here is if you are applying two hops, you can simply do one hop for the current element, and if required, the next hop can be taken afterwards, and it will lead to either same or better results, right? So that is the claim. If you don't get it, I would encourage to try it out yourself and try to convince yourself that this statement is true. If you face any issues, we can discuss it in the problem in the comment section below. Okay. So now we know that we have to apply one hop. So in every operation, I will be doing, or I will be fixing at least one element. That is the first element. Okay. So let's say what you will do, you will just do, okay, I will move one to its small, like I will move the smallest element to the first position, and whatever position of that smaller element would be, I will replace that with the current element, right? Just swapping. Now the problem is reduced. We are now saying that I want to sort this particular array, and like with minimum number of operations, right? So this is exactly same as the original problem. We will again do the same thing. Just take the first element, swap it with the smallest one. So smallest one is 2 here. So you just swap it with this element. 2 will come here. This will become 10. And now you will say, okay, now I have to sort this particular array. So notice that you are solving the same problem. Just so the approach is start with the first element, replace it with the smallest one, and then move forward with the next element. Okay, so that is the approach we are following. Remember, we are able to follow this approach because we have intuitively seen that follow like directly moving directly moving an element to its correct place is as good as, at least as good as, moving it in 2 or 3 hops. Okay, so that's the solution. Now if you think about it, you have to find minimum element in the remaining array, right? And you have to replace the element, replace the position of particular element as well. So what kind of data structure you will use? So there are two operations, or rather three operations. First, find the minimum, right? Second, remove the remove one particular element, like either 9 or 1, right? Like let's say you replace 1 with 9. Now you have to remove this one from your data structure altogether, because 1 is now done, right? So second is you have to remove a element. Third is you have to insert a element, right? You have to insert an element at a particular position. Like position is also like you have to insert an element at a particular position. So these are the three operation that is required. Now if you think about it, these two can be done using mean hip as well. But now inserting at a particular position, this is something that you like and there is fourth operation as well. Like removing, you are not only removing this element, you have to remove this element as well, right? So you have to remove also from a particular position, right? So basically this three, the first three operation can be done using mean heap as well. But if you have to perform this operation as well, you need set data structure, because set would help you remove anything from any position in login time. Okay, so let's look at the final solution with set. Let's say you are maintaining a set of pairs. So you maintain 9 0 10 1. This second one is the positions, right? Now like as discussed, we will remove one with the smallest element. So set can give you the smallest element in order login time, right? So you found out one, you remove one from here, you remove 9 as well. Now what you will do, you know the position of 1 as well. Position of 1 is 7. So what exactly you have to do, you have to increment your result. Your result will incremented by 1. Okay, and you have to remove 9 from 0th position and insert 9 at 7th position, right? This 7 you will get from here. Now basically what you are saying is this is replaced by 1 altogether, and this becomes 9 altogether, and this is your data structure for the remaining array, this array. Now you will apply the same approach again. Take the first element, remove it, replace it with the smallest element. Smallest element is this. Take the first element 10 1, and now you will replace it with 2. Like 10 will be replaced by 2, and 2 will be replaced by 10. So how you will replace in your data structure, you know the position of 2. Position of 2 was 2, so you will just add 10 comma 2 to your set again. right? So that's how you will perform the operations. And if let's say at any position you are seeing that you don't have to perform any operation, you just move forward. Okay, so hope you got the solution. If let's look at the code quickly. Again, I would encourage you to do it yourself first, and then we will and then come back here so that you understand it bit better. So what we have done, this is standard BFS for finding out the number of nodes at each level. Okay, we will look at it in some time, but let's first look at the other function which says what is the minimum number of operations to sort a particular array. Okay, so what we have done, as discussed, we have prepared a set of value and indexes. We pushed every value and every index here. Now we start with the first element. We figure out what is the minimum value that we have in the remaining array. So remaining array is equals to remaining set, right? Because we are removing the elements from the set as well. So we figured out what is the minimum value there, and we erased that minimum value because remember we have that minimum value would not be there anymore, right? That will be removed from your working set. So after that we saw that whether minimum value is the current position or not. Okay, if it is, we will continue. We don't need to perform any operation. Now why we are able to do this? The reason is we are able to do this without checking indexes. Like index also we can check, but we are able to do this without checking indexes because it is given that each value is unique. Okay, I would encourage you to think about it and how this will change if value is not unique. Okay, so that is an exercise you can take. Let sort like perform the same question, just that values are not unique. Okay, so for now, like values are unique, so we'll continue here. We will not perform any operation. Otherwise, we have to perform one swap, right? Because we know the current element, we know the current position is not equals to the smaller one. So we have to perform one swap. So how you will performing one swap? You are erasing the value, the current value, or basically the value at the current position. So uh, in this case you are erasing 9 comma 0, right, and inserting 9 comma 7. So that's what you're doing. You're erasing the value at this particular index and you're inserting the same value at the new index. Okay, and finally you are updating your array as well, because remember you have to update your array to 9 as well, so that when you come here you know that 9 was here. Okay, so that's it. Like that will solve for how many operations you require to sort an array. Now let's just quickly go over the code of BFS as well. So that is very standard. We pushed the first route to uh, our vector. Now we are iterating over everything here. So what we are doing, we have pushed this first route in our vector. Now we are iterating over everything or every child of this node and pushing it to a different vector. Okay, so initially this would be there in your vector, and you will be pushing 3, 14, and 10. Okay, and after that, let's say 3, 14, and 10 was there, so you will be doing the same operation for all of these first. So you will take 3, push 5 and 4 in your vector, take 14, push 2 in your vector, take 10 and push 1 in your vector. And once you have done that, you can move forward with the next vector. So what you are doing, for every node in the previous level, you are finding out the children of those nodes and pushing it to a different vector. So that's why we have two vector here. First is the level which denotes the number, the nodes at the current level. So initially there is only one node, that is root, and then we are finding out next level, the nodes at the next level. So what we are doing, we are iterating over all the nodes at the current level and just pushing their left and right, and also maintaining a vector of current node values. So finally, we will have current level will contain all the nodes of the current level. Next level will contain all the nodes of the next level. Okay. So because we are checking we will just replace the level with the next level. Like this is the new level now, and we are maintaining all the levels, the value of all the levels in a single vector levels. So we will just push there, and finally for every vector in this levels, I am calling minimum operations of I. Okay, so hope it makes sense. If you have any doubts in this problem, please post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe to the channel if you haven't already. And I will see you in the next one. Thank you.